So, gentlemen, today, this morning, I'll be introducing us to sewer and stormwater design. So we'll start with wastewater discharge and collection. So here, so let me start with hydraulics. Okay. So let's start with the hydraulics of, so open the material for hydraulics. So these are the components of a sewer system. In a sewer system, you have the gully inlets, you have the pipes, you might have the manhole, and you have the special buildings, such as overflow structure, siphons, drop structures, and everything. Then you can also have the pumping station. Usually, the pumping stations are located at the treatment plant. Now, this is how it works. Your sewer line collects sewage from residential areas and transport them via gravity. It must be gravity. Unlike in water reticulation, where we say we have a pumping system and a gravity system. In the case of sewer, it's going to be gravity. There's no two ways about it because of the energy requirement again. So it transports things by gravity. And because those wastes are going to move by gravity, your treatment plant, your wastewater treatment plant, is likely going to be located at the lowest part of the city. Remember, in water reticulation, your overhead tank, your reservoir, is located at the highest part of the district, the city, the catchment. Okay, but in the case of sewer, it is the reverse. It's going to be located at lowest point so that the water can flow by gravity. However, when it gets to the treatment plant, in most cases, you now see that you need pumping to pump it back to the ground level. In the case of Abuja, for instance, the difference between the normal ground level and the intake of the treatment plant is about 12 meters. So most treatment plants are always located, especially intake of the treatment plant is only located at the lowest point. Then you now need to use the pump, and the major pump they use is what they call the Archimedes screw pump. The Archimedes screw pump or the sewage pump. But the sewage pump is known to block because you are talking about raw sewer. Sometimes you see dead bodies, sometimes you see dead animal, sometimes you see all sorts of things in your sewage system. It's a terrible place. So, but the Archimedes screw, the Archimedes pump is a type of pump that makes it easy, that clogging is almost impossible. You hardly okay. This is Archimedes screw pump. So this is what it looks like. The Archimedes screw pump. This is what it looks like. The idea of this Archimedes screw pump is to prevent blockage and then to save energy too. Because it's not like a pump that uses a blower system that uses, this one is like a very, very subtle system. So this is what the Archimedes screw look like. So I don't know, like here. So this is just what it is. This is every treatment plant, this is what it uses. Like it's not negotiable, gentlemen. So if you're asked to design a treatment plant, just know that to take water from your intake to the treatment plant located within the same place, you must need an Archimedes screw pump. That is just what it is. If it is water, you can use a sewage pump, you can use an off-fleet pump, good. But for this case, I tell you, because the raw water sewer is coming with a lot of debris, it's coming with a lot of suspended materials. So if you use conventional pump, there will be abrasion, there will be wearing, there will be a lot of stuff. But with the Archimedes screw, you are safe. So please, just take note of that. Then, of course, the pumping station is usually located so that you can pump water from the lowest point to the highest point. Then you have infiltration structures. Most times, when after treating your water, and you know that you have removed some of the BODs and CODs, okay, either by infiltration or everything, you can pour some on the surface so that they can infiltrate the ground because they are safe. There's no contamination with groundwater. The wastewater treatment plant is always referred as WWTP. Manholes are for inspection, of course. Your pipe is to convey them. Your gully inlet is also to let in the flow. So these are some of the gully inlets. It's a collection of runoff. So gully inlet are usually for stormwater. Okay. So this is what a gully inlet look like. Remember, these are the gully inlets you see on the road. Okay. So it's for stormwater. So it's to collect runoff from street and from road. Okay. It's also meant to retain sand, so that at the end of the day you can dislodge them, you can remove them, you can desilt them. Then, okay. So the other thing is that most times we recommend in our gully inlet that you don't use a pipe less than 150 mm. And then your gully should not be spaced more than 45 meters apart. So this is what the gully inlet looks like. Then for the pipes, we have closed pipe and gravity flow, and you hardly use seldom use forced pipes. Then the cross section can be circular, it can be X-shaped, it can be mouth-shaped, it can be rectangular. What influences your choice of cross section is usually the amount of wastewater. It's also a function of the slope of the sewer. Also, the variation of flow. Then also the depth of sewer also influences that. The depth of sewer also influences your size of pipe. Then also the static and dynamic load also influences it. You don't put it too much on the surface. If not, dynamic and static load will affect it and it will break. Then for ease of maintenance and operation, you also have to put it in a place that you can recover it. So these are some of the typical cross-section pipes, sewer pipes we have. Okay, so these are just some things. Okay, how do you construct sewers? You talk about open trench construction. Okay, however, the limitation is that if you have a limited depth, it can be a hindrance to traffic and all that. Then, okay, so if you do trenching, it's easy to pump out water. It's easy to lay your pipe and everything. But if it is strengthless, strengthless construction and tunneling are the ones you do under. In most European countries, you do it under the buildings. Traffic does not affect it, and it does not depend on building. Okay. And so on and so forth. So this is a sample of laying a pipe, like a sewer. This is a sewer pipe, definitely. Okay, so sewer materials. There are a lot of sewer materials you can use. You can read all these things. I don't need to go through this. Okay, for sewer layout, like I said before, here it says minimum sewer you can use is 250. Yeah, but sometimes 150 is the standard, but this is just the recommended. Okay, but the standard says you should not use less than 150 mm. And it says that if anywhere you change diameter, you must introduce a manhole. Okay, you must introduce a manhole anywhere you change diameter or where you have multiple pipes connected. Okay, so some of these things is what we can read. I don't need to bother. These are graphics of a typical manhole. Okay, you look at the entrance shaft, look at the access and everything. I mean, you can read this to understand it. This is the cross section of the manhole. Okay, you can see where the sewer pipe is laid. You can see the steps where you can enter here and maintain it if there's blockage and everything. You want to put in a pipe cleaning mechanism. This is how it is done. Okay, and the manhole should just come in between this. So I think we can view all these things and read them. So this is a typical manhole where we have 2 or 3 pipes coming together. Okay, yeah. So it must have access and it must have that kind of shape. So what you just saw here is just what is here. So for this one, you can see that this is a typical stormwater drain, underground stormwater drainage. Some cities, when they don't have space on the surface, they go subsurface for their groundwater, especially places like Paris, where they don't have space. Most things, the metro stations and many things are all underground. So the sewer also goes underground. So it's advisable that your bend should be at a angle 45. There's nothing like angle 90. You must not do angle 90 in pipe. 45 is advisable. So inspection chamber, what are they for? They are for aeration, they are for access, for inspection, for cleaning. Okay. So and so on and so forth. Okay. So here it talks about basis of pipe parameters. He said the flow cannot be calculated except exactly because of inaccuracies in duct laying, influences of manhole, etc. Wastewater is usually discharged by gravity flow. Force sewers are used only in special cases, almost in no cases. Just ignore. You only use force. Pipes is always an open system for stop anyway. And the other one is flow by gravity. So here we said variation. We said that we have what we call dry weather flow, QDW. Dry weather flow is the flow when there's no storm event. That's why we say dry weather flow. If there's no storm event, what flows inside the pipe is known as dry weather flow. Then QR, anywhere you see this QR, it means runoff. Arrow in our context means runoff. And when I say runoff, I'm referring to storm events. Runoff has to do with storm event. Runoff has to do with land area. Runoff has to do with rainfall. Rainfall comes in, it gathers, and it goes as a runoff. Okay, so when you see WW, it means wastewater flow. All right. When you see QDW, it means dry weather flow. And when you see QR, it means runoff. So we are back to the same basic calculation we have, that if you multiply velocity by the surface area, you have Q. If you divide Q by the area, you have the velocity of flow or the discharge. So Q will be in meter cube per second or meter cube per hour, while velocity will be in meter cube per second. Please, this is a standard Dicey equation, which is the basic for every hydraulics. So this is Weisbach equation, which says that frictional losses is directly proportional to the length and inversely proportional to the diameter. Also directly proportional to the square of the velocity. Remember, I think we know all this. This is something we already used to. So there's another formula for frictional factor called the Van de Broek equation. However, all these equations have been converted into charts. So with the right chart I'm going to give you, you don't need to cram any of those formulas again. Okay, so all these, you can read them and you understand them. I don't need to go through them. There's nothing here. This is an example of what we call outfall structure. Outfall structure is where the sewer or the stormwater joins the open stream. Where the sewer, this is stormwater, this is about 900 mm pipe. So you can see that at this point, this water is joining the open stream. So whatever water is coming here is already a stormwater. So you can also have wastewater coming in this form, but in that case, it must have been treated in a treatment plant. Must have been treated in a treatment plant. So all this we can really understand. Types of pumps we use in sewer or stormwater design. Okay, so it talks about rotary pumps. It says it's often used in wastewater pumping station due to simple construction and good efficiency. Rotary pump. I can tell you that Archimedes screw pump is also a form of rotary pump.
All right.
The other one says okay. The other one again is it has a lot of shapes. So the advantage again is that it can come in different shapes. Then we have the displacement pumps, which comes in form of piston pump, eccentric pumps, and so on. Used particularly in wastewater treatment plants for conveying sludge water. Displacement points are used for conveying sludge water, especially in biogas plants. Then you have the screw conveyors. He said there are robust pumps for large flow rates and small pumping head. Okay, I think the Archimedes screw fall into this one. So they are usually, they don't have too much head. 12 meter, 10 meter, 15 meter, 18 meter, which is normally the difference between the position of the treatment plant, the position of the intake of the treatment plant to the primary sedimentation basin. We'll all come to that. So he said it's usually used for lifting inflow of a wastewater treatment plant. I want us to understand something. In every wastewater plant, there's always a point where you have to lift the water because the water is coming by gravity. So by the time it will flow from the highest point in the city to the position of the treatment plant, it must have gone down very well. Like I said, the one in Abuja is a difference of 12 meters. We are talking about 3-story buildings or 4-story buildings. From where the water is coming, where the water finally lands, to where it is needed to be treated. So you must have a screw pump to lift it up. So call them lift pump, but they are low head lift pump and they are screw pumps. So these are just examples of some of the pumps we've treated. Okay, rotary pumps. These are samples. These are how they are. You can change them at every point. So these are submersible pump. These are seaway submersible pump. Very, very versatile in use. This is what is mainly en vogue in most conveying sludge, especially treated sludge, in between the different component of a treatment plant. So this is a wet arrangement of a rotary pump. So you can see the pump here, located here, with the motor on top. Remember, this can be submerged. The motor units are protected from water and everything. So this is what the construction look like. Okay, provide ventilation, provide control, and what have you. So this is a wet arrangement. In other words, it is submerged, and then this is a dry arrangement. Dry arrangement is not in contact with water, but the water is here. So this one means you cannot overflow this. You can't flood this one, but the first one you can flood it. So this is an example of a displacement pump. That's what it looks like, and that is the operation mechanism. Displacement pump. Then here is the screw conveyor, Archimedes screw, which I just explained. In every treatment plant, you must see this pump. You must see this pump because of its previous. The advantage is that the flow rate, it has a large cross section. Okay, it says it has a non-destructive conveyance. In other words, it does not. It keeps the wastewater the way it is. From here, the wastewater will move to the screen. This is the raw water coming here. This is the raw water coming from the city. Then it will be conveyed here. Here you will see tissues, you see human hairs, you see blood, you see every sort of thing. Then once it comes to this point, from here it enters, it starts the treatment journey. And the first step is that it will go through a screening where all the dissolved solid, all the suspended solid will be screened out. And then after screening it out, it goes through the grit chamber. The grit chamber is where you remove the grease, you remove the oil, you remove the suspended sand, because you don't need your sand to go into your treatment plant. Then from there, it now goes into the primary treatment plant, or we call them the aeration tank. Okay, and that's the first thing. You stay there for some days or for some hours while being aerated. From there, you move to the secondary. From the secondary, you remove nitrogen, you remove phosphorus, you add whatever you want to add, or you reticulate it more. From there, you move to the effluent, or you move to the denitrification or other, depending on what you want to remove from the treatment plant. When you have reduced the POD and the COD to acceptable level, where it will not damage or distort aquatic balance or kill fish, you know what I mean when I mean aquatic balance. There are also, it does not pose immediate risk to the open stream. That is when you now discharge it into the open stream. One thing about river system is that the river that started here can be used by 100 communities downstream until it flows into the ocean. So that's why you must maintain the river, the health of the river. And not just about the fish, the living organism that require the water to exist, but also those who might need it at the downstream for either for agricultural purposes or for domestic purposes. So this is Archimedes screw pump in action. So these are some of the efficiency of the pumps and everything. Okay, I will not go into that. I think we can already do this. These are about losses. Okay, and the head. These are about pump operation. We've done this before, and that is all for that. Then I go to hydrology. When you talk hydrology, what comes to your mind? Hydrology has to do with water cycle. Period. Hydrology is basically about water cycle. Why do we understand the water cycle? We need to understand the water cycle because we are talking about storm water, storm events, runoff. We're talking about the storm event runoff. So that's why when we talk about storm water, the pipe sizes are now going to be bigger because you are referring to the water cycle. So this is a typical example of what urban hydrology means. We are going to find out how do we convey the precipitation that's coming in form of rainfall, snow, and hail. How do we going to confidently convey them into a discharge or the open stream? That is what stormwater design is all about. So how does rainfall runoff form? Through wetting, after wetting, after evapotranspiration, after depression, storage, after infiltration, then you will now see runoff. So when water falls, some will go into wetting, some will wet the leaves, wet the plant, wet everywhere. Some will go back into the atmosphere in the process known as evapotranspiration. Then some will also infiltrate. Okay, then the remaining one that cannot infiltrate will now run through the surface as what we call runoff, and then you need to design a drainage to be able to convey them. So there are parameters we must discuss when we talk about rainfall or stormwater design. So now we are in stormwater design. The first thing is that
you are not that audible. We can't hear you.
There's something we call duration. Every storm event, when I say storm event, I'm talking about rainfall, just a technical word. Rainfall. Every storm event or rainfall has what we call duration. There must be duration of rain. That's a key factor, key parameter. Then you must also discuss the height or the depth. The height or the depth of rain is something you do using your rain gauge systems or use your measuring system. There must be that. Then there must be intensity. But basically the intensity is just dividing the height over the duration. So if you divide the height by the duration and it's giving you a high value, you know that that is a very high intense rain. How do they predict flood in developed countries? Very simple. Once they measure the depth over duration and it exceeds a certain threshold, they will declare early warning system for flooding. Let's say the baseline is always 100 mm, like Abuja. Abuja is around 120. That's for that one is even for 25 years return period. For basic rain of 2 years return period, Abuja is around 100, 110. But let's say 100. Lagos is around 120. So if I divide the height of rain divided by the duration of rain, I should be able to see something below 100, 120. If I do it and I got 200, I will declare flooding. I will anticipate flooding. Flooding doesn't happen just immediately after rain. No, it speculates. It's kind of upgrade itself by people living downstream. So if it's going to flood, like in the last 5 days, I learned that Lokoja is flooded. Okay, it didn't flood at once. It is the rainfall coming from the River Niger, from Kebbi State. So at the start from Kebbi State, even beyond Kebbi State, at the borders of Nigeria, it might take up to a week to reach Lokoja. So when people in Kebbi State notices that the rain, instead of getting 100 and they're getting 200, they will signal those in Lokoja because Lokoja is the confluence, is a flat land. So as the flood is coming down, is aging. As it's aging, the height is coming up. The height is going up small, small, small. Once it reaches somewhere that is very flat, okay, the height will submerge things. So intensity of rain is very, very key. The fourth parameter and the final one is the frequency. The frequency of the rain. When you do design for stormwater, you must ask yourself, what is the design period, the return period? That return period in the impasse of it is what we call the frequency. The return period can be 1 year, can be 2 years, can be 5 years, can be 25 years, can be 50 years. In 2013, there was a flooding in Lokoja. Experts estimated that that was a 50-year flood. Let me repeat it again. There was a flood in 2013 in Lokoja that stayed for many days and submerged many places. It was estimated that was a 50-year flood. What do they mean by 50-year flood? What they are trying to say when they say 25-year flood, 50 years of flood, 20 years flood, 5-year flood, 10 years flood, it is the frequency, the probability of that flood occurring. That's what they mean. How do we say it was a 50-year flood? Because the last time that flood happened was in the 1960s. Those who are alive in Bayelsa testified to that. They say the last time we experienced that kind of flooding was like 50 years ago. It means that this kind of rain comes at least once in 50 years. So when I say my return period for my design is 10 years, what I'm trying to say in essence is that I'm designing a structure, I'm designing my pipe system such a way that in 10 years, if this kind of rain should come, my structure will be able to hold it. So that is just more like a safety factor. Now, when we start, you will see a table where, depending on what you are designing, what you are meant to use. Most times, to design normal storm, you use 1 year, 2 years. You know why? Because the rain comes every day. The rain comes. So, but in some cases, when you're designing against, maybe for big cities, like when Julius Berger designed Central Area, he designed for what I call 20 years flood. From what I've seen, that's why you see their sewers, their channels, everything is very big. And I do tell people that it will never flood in Central Area. It will never flood in a place like Manhattan in New York. Why? Because these are high-brow areas. So everything they've designed there, they've captured in that if there's a probability of flood, the losses, the insurance companies are going to pay massively, or the catastrophe will be so massive. But if you're designing for rural areas, you don't need to use 2 years or 5 years. No, just use 1 year return period, because the possibility of flooding is low. And even if it floods, nothing will happen. It will just flood farm areas, and within days, everything will percolate. But when you're talking about big cities, center of towns, of most cities, they use a very high safety factors, because, and that's why most of them are underground, not surface. Because underground, they can build 2-meter diameter pipe, they can build 1.5-meter diameter pipe that can be able to hold the entire storm water in the city up to a 10 years flood. Very, very important to understand when and how to use the return period of your rainfall. So we also try to classify rainfall. We said any rainfall that is up to 650 hectare per year is classified as a weak rain, and heavy rain is the one that's where the rain is. This is an old formula. I'll give us the new formula. Let's forget this formula. So this is what a IDF, what we call IDF, intensity, duration, frequency curve looks like. Okay, here you have the intensity of rain. Here you have the return period. So now, if this is like a 6 minutes, for instance, in a 2-year return period flood, it might be 5 mm per hour, but in the 10 years, it's about 10. But I'll still explain this further. So there's what we call time factor. Time factor is a factor that averages intensity, duration, and frequency in one whole number. Okay, I'll still come to that. Okay, so for example, for instance now, the rain intensity denoted as R in Germany is usually between 90 to 130 liters per seconds per hectare. I repeat again, 130 liters per seconds per hectare. Okay, however, This relationship holds for frequency between 0.05 years to 4 years. That 4 years, 4 you see there, is, if you're not talking about the frequency, it will be 1/4. And 1/4 is 0.25. So that 0.25 is the frequency. In other words, there's a likelihood of that flood happening 0.25 times in the year. Okay, or once in 4 years. So I've talked about this before. Now, there's what we call runoff coefficient. Please pay attention to this. This is very important. There's what we call runoff coefficient. If you are designing for a stormwater, for instance, stormwater is dependent on many things, many factors. Number one, we have what we call pervious and impervious area. The area that generates stormwater are the impervious area. So if the impervious area is huge, you're going to generate huge stormwater area. You're going to generate huge stormwater. If the impervious area is low, you're going to generate less storm. Okay? The impervious, either you call it paved area or impervious area. Then the second factor that influences stormwater is what we call the surface type. If you have an impermeable surface or impervious surface, all the waters that fall on it will generate runoff. But if you have surfaces that are not paved, that are unpaved, or that are pervious, then the stormwater will be less because there will be a lot of infiltration. And remember, we said it is after drifting, wetting, evapotranspiration, infiltration, depression that you now have surface runoff. So that's why in city planning, they encourage people to plant flowers to have infiltration basins. I remember those days when things are very normal. If you take your drawing to the main control in Abuja, they will want to see some level of gardening. If you pave everywhere, they will reject your drawing because they want you to provide for infiltration areas so that not all the water that falls in your plot will come to the open drainage. Because if all the waters come to the open drainage, then it means you require a lot of huge drainage or there will be flood. So they expect that you put some form of interlock, gardening, and not just to cement everywhere. But what we've seen these days, you will see people cementing everywhere, thereby increasing the risk of flooding. And that's also why you have green areas in cities. So that sometimes when there is huge rainfall, those areas will help take some rain, impound them for a while, and then they will infiltrate. But if you have everywhere paved, then there's possibility that you have a high runoff. That's why in many cities where everywhere is paved, once it's raining, you see the streets, you see everywhere flooded because there's nowhere the water can percolate and infiltrate. So this is part of what urban design entails, of course, which we're abusing. Then also the slope of the area. The increase in area will increase runoff. That's common sense. Then the rainfall intensity will also influence the runoff coefficient and as well as the duration. Then the type of soil and vegetation. Clay soils are impermeable. So when it rains where there's a lot of clay soil, it's likely runoff will be higher. If you have where we have sedimentation basins or sedimentary sand, there's possibility that they will percolate, they will enter into the ground, and there will be less runoff to be generated. For instance, if you have a roof, a slated roof, slates like carbon roof, the runoff coefficient is about 0.95. In other words, it means that the 95% of water that falls will flow. That's what it means. While gravel parts, if you have a place you just pour gravel, okay, it's a virgin land, it's a topsoil, and you just pour gravel. The runoff that it will generate would be like 15 to 20%. While your roof will generate almost 95%. That's what this place is talking about. So you can see that not every material generates the same runoff. Very important. So this chart now is trying to demonstrate how slope affects runoff. The summary of it all is that the higher the slope, the higher the runoff. So normally this is how you do the formation of runoff, okay? So imagine that this is your street inlet. So as water falls here, the head goes here. The discharge is around this place. As it flows to the second building, the discharge builds. As it flows to the third one, the discharge builds, and so on and so forth. That's how the discharge will be building. So this same thing also is how sewer flows, because they are pipe flows. So if you have a house is connected to a central sewer or a central sewer line, as it's going downstream, it is increasing in the discharge. So as the discharge is increasing, that means the pipe will also be increasing, just like we had last week. So this is the formula for runoff. When we say runoff, runoff is simply the rainfall intensity multiplied by the runoff coefficient, multiplied by the time factor, and then multiplied by the surface area, or we call it the catchment area. Okay? However, the frequency and the duration have been captured by the time factor. So time factor takes the place of these two people. Okay? And when you see something like this, rain intensity, arrow 15, 1. What does it mean? It simply means 15 here means the duration is 15 minutes and the return period is 1. So that's like normal design, normal base design. We usually use 10 minutes or 15 minutes to estimate our runoff. That's to say, the first 15 minutes of a rainfall will determine whether there will be flooding or not. I've said it severally. This is how these predictions are done. Okay, so from the map, you can get the area A. What's the catchment area? Okay, then the percentage of impervious area, the slope of the catchment area, and the rain intensity are now determined using the rain runoff coefficient. Okay, we're done with that. Okay, let's go. For what wastewater? So I'll be using two words distinctly here. I'll be using wastewater. When I say wastewater, I'm talking about sewage, and I'm talking about the anthropogenic activities happening within residential areas. The water for your cooking, sorry, the water from your shower, toilets, the toilets and your shower, of course, the toilet from the water from your kitchen, all of them. Let me just say the typical water that goes to your septic tank in your house, these are sewage, okay? And I'll be calling them wastewater. They are the wastewater. The shower water can be called gray water, but they are also part of wastewater. Then we have the stormwater. So for now, let us focus on sewage first. So on wastewater or sewage. So the wastewater flow is the daily flow plus infiltration flow. Infiltration flow is important because these are the waters that flows into this pipe sewer, uncalculated, unseen, unaccounted for. Those are what we call infiltration. Okay. Then dry water flow, when you see QDW, means dry water flow. Like I said before, these are flow in your sewer network when there's no storm event, when there's no rainfall. The water that is flowing in your sewer is what we call a dry weather flow. In other words, the flow when weather is dry. Then we have what we call a combined wastewater flow. When we say combined means sewer and stormwater combined together.
Yes, sir.
So you have question? No. In wastewater flow, we will talk about liters per capita per day. The input parameter is your drinking water requirement. So if I ask you, what is the quantity of sewer? You don't need to clap your head. whatever is the drinking water requirement automatically becomes the sewer discharge requirement or whatever. Because it's garbage in, garbage out. What you take is what you give. In Germany, they don't charge you for wastewater and then water is differently. No, because the assumption is that what you drink or what you consume is what you produce. It's not disappearing. So when they give you 100 cubic meter of water, they will charge you 100 cubic meters for wastewater. They will charge you that immediately because it's assumed that you use them and discharge them back. So it can also be for unresidential areas. It can also be liters per hectare per day. Just like we said last week, you can design based on population land use. What is the land use? What is the size of the land? I can say, okay, this is the water drinking water requirement per hectare. Then also for industries also, we say liters per production per day. Rainfall intensity is liters per hectare per seconds. Okay, so the total discharge can be in liter per seconds, meter cube per seconds, meter cube per hour, meter cube per day, or meter cube per annum. So it depends on how you are aggregating. So this is the domestic wastewater production, which is also can be likened as water intake. Okay, in Belgium it's about 122. In Nigeria, remember we say it's 100. Okay, you can see some countries are really wasters of water. People like Canada, USA, Japan, they really waste a lot of water. So, but here we say that the specific wastewater production is specifically between 100 and 250 liters per capita per day. Between 100 and 250. So you can use 120, you can use anything. But that's what it is. So some of these values are stated here are what they also put in Germany. Like they say 130. 130 is for Germany. In Nigeria, we're using 100. So if you now want to get the daily total water discharge, you multiply the population equivalent P by the daily wastewater discharge. I mean, we did it last week. So these are the specific wastewater production in Germany. Okay, 130 for average proportion, 150 to 170, and then for proportion of small trade between the average of 100 and 130. Okay, I think you can read this one, understand them. So back to wastewater production. This is just an example of a table we shared last week. For hospital, their wastewater production is about 250 to 600 liters per second. Okay, per bed, sorry, per bed. Swimming pool is between 150 and 180 liters per visitor. You know, when you multiply by 1,000, you get liters. 1,000 liters equals to 1 meter cube. For school, it's about 20 liters per people. The environmental store is very small. It's not everyone that comes to the shop that goes to use the toilet or discharge anything. So it can be 10%. That's understandable. Restaurant, that's the value there. Then hotel, I've said that one, and so on and so forth. Okay. So this talks about infiltration water. Infiltration water means water that infiltrates into the pipe network of a treatment of a sewer line. If you lay a concrete pipe on the ground, like Abuja, because of aging of pipe, when it rains like this and you go to the treatment plant in Abuja, the discharge will be so massive. And the problem is groundwater entering the sewer line. So in most places, the water will jam the water will meet groundwater, and those groundwater might find their way and go into the pipe. This is a common occurrence. So we're talking about you need to make provision for infiltration water when you are designing your sewer or stormwater. Okay, I think we should that's the end of the introductory class on that. I don't know if there's any question. So the next thing I will introduce you is your Nigerian Code of Practice. Let me introduce the Nigerian Code of Practice. So if you open the Nigerian Code of Practice, like I said, it's a very important document that gives you the runoff in every city, in every major town in Nigeria. Okay. For instance, this is Makurdi. This is Makurdi. So if I want to do design for Makurdi, I don't need to go asking water board to give me values to give. No, all I need to do is to get this material developed by the Federal Ministry of Works about 6 years ago. No, sorry, about 12 years ago when Goodluck was still around. Okay, so if you go here, you see that on the horizontal, you have the duration. So the horizontal is about what? The duration. The horizontal is the duration. So the duration on the horizontal, then on the vertical, you have the rainfall intensity. So with the rainfall intensity and the duration, you now read off based on your return period. Okay, this is Mina. This is Makurdi. And this is Mokwa. When did I leave Mina? Okay, whatever. Let's use Mina. Whatever. So here, this is the duration. This is duration. Here is 6 minutes, 10 minutes, 15 minutes, 30 minutes. We usually focus on the first 15 minutes of frame to do our design. That's the standard. So now I will now measure it against what am I designing for? The first one says sewer, 1 year. Second one says two-year return period, 5-year return period, 10 years return period, 25-year return period, 50-year return period, 100-year return period. The return period you use is a safety factor. If you use a higher return period, it will give you a bigger pipe size. So be careful. That's why we say that safety factor is a political decision. Okay. If you're not designing against flooding, you have no business designing anything above 10 years. You can design for 2 years, 5 years, or even 1 year. Normal sewer, normal stormwater drain in front of your house is a 1 year. You just use 1 year. In other words, from 15 minutes, I read off, I go here, and I can say 90 Mina, rainfall intensity in Mina is 90 millimeter per hour. 90 millimeter per hour. Are we together? 90 millimeter per hour. But if they now said, oh, it's flooded in Mina or some special hydro areas in Mina where they never wanted to flood because of insurance purposes, they now say, oh, designed for 25 years. It means the value I will use will now be 160. So you can see I have moved from 90 to 160. If you use 160 to do your design, if you are getting a channel of 1.2, the person who used 1 year will be getting a channel of 0.6, which is what I see most developers do. It has become a norm for them, whether in the east or in the north, everywhere. Anywhere they just say 600 by 600 meter drain. But because they are designing for a low return period. But once you start designing for a high return period, then your sewer, your sizing will now become very big and massive. It will become big and massive. So one need to be careful. That is where engineering comes in. That is where you, the consultant, need to know what you have to use so that you get it right. So this is how to use the intensity, duration, frequency curve. So once you get this value and you multiply it by the coefficient of runoff, multiply by the surface area, you automatically will get your runoff value discharge. With your runoff discharge, you now go to our chart, that's our usual chart. and you read off the size of the pipe. So once you get the surface area of the pipe, you now decide to use whether circular pipe, rectangular pipe, or trapezoidal pipe. It's very simple, gentlemen. Okay, so that is the standard code of practice, like I showed us. Okay. So the next thing I want to show us is what we call, let me introduce us to the rational method, so that from next week, we'll start the calculation. This is rational method chart. No, let me introduce us to rational method. The rational method, like I said before, is an age-long method to design pipe for sewer and stormwater. Even though it has its own limitation, normally people will tell you for any catchment that is below between 75 hectares and 150 hectares. Once it's above 150 hectares, then you have to use empirical method. So this is the rational method. The rational method is, this is a catchment. I'm giving a catchment like this. Okay, I'm giving a catchment like this, and I'm asked to design the sewer. Let's say the treatment plant is here. So let's start with sewer. This is treatment plant. So here is catchment A. This catchment A means there are houses here. There are houses up and down, houses here, no matter the arrangement. But I'm assuming that this pipe is the pipe that conveys their wastewater. It conveys wastewater from here. It comes here. The one from catchment C joins it. It comes here. The one from catchment E joins it. It comes here. The one from catchment G joins it. And then finally, it goes to the outfall at catchment H. Okay, so if I calculate the whole total sewer here, I will add it to this place. When I come to this point, okay, like I said, this is catchment B. I will calculate the whole value of discharge. I'll simply multiply the rainfall intensity here by the surface area. That will give me the level of water that will fall in this catchment. I will add it to the one from A. That becomes the value here. When I go to 0.2.1, I will go back and calculate the discharge of catchment C. Add it to the discharge of catchment B. That becomes the discharge of catchment D. When I come to catchment F here, I will come back again. I will calculate all the discharge in catchment B. I will now add it to the value I got from catchment D. That becomes my new discharge at catchment F. When I come to H, I'll calculate all the discharge in catchment G. I'll add it to what I got here. That becomes the value I will get here. And then from here, I'll add it to the value of catchment H, and then it will discharge here. You need flow Q to get your A, because Q equal to VA. Don't forget that formula. This is the basic formula in hydraulics. Q for discharge is equal to velocity times surface area, or it can also be Q, small q, times A. Our interest is to find the value of A. What is the surface area that will be able to discharge this volume of runoff, or that will be able to convey this volume of wastewater into the treatment plant? So from this example we got here, you could see that these are the conduits. You have to relate this with this. Maybe, gentlemen, I'm going to do something so that I will do it well. In next week's class, please, you have to print this. You have to print it and have it hard copy. Remember, this is online training, so sometimes it has its limitation. There are some things I want to explain or talk about. You need to hold it in your hand. Okay? What you have here are exactly what is being represented here. So, for instance, this is catchment A. This is the border of catchment A from here to here to here to here. The area is 15 hectares. The area is 15 hectares. Catchment B is 5 hectares. Now, if you go here, you see catchment B is not as big as catchment A. It's 5 hectares. Catchment C is as big as catchment A. Look at it. That's why the value is 14.06 hectares. Catchment D is even smaller than catchment B. Look at it. While catchment E is going to be like catchment A. Catchment E is almost 14.84. Then the other catchment that is very big is catchment G. It's almost 14 too. You can relate. So you can see that as you are going down, the pipe size is increasing. It's increasing. It's increasing. If you use the same pipe size all through, there will be blockage. It's a wrong design. And this is where engineers failed it. You see somebody doing a sewer design, you use 150 mm all through, or use 200 mm all through. It is not possible. It's a wrong design. The value will increase as you are going downstream. As more catchments are connected, as more houses are connected, your pipe size will move from 150 to 200 to 250, probably at 300, depending on the distance and the number of houses. Sometimes it can go as high as 600. That's why you now start using concrete pipe. Very, very important. Then this is the slope of each catchment. 1 in 200. 1 in 200 simply means 1 over 200. So that will be 0.0005, whatever. Okay, so these are the slope. Now, when we mean the slope is the beginning and the end in each catchment. So it means from here to here has a difference of 1 over 200. In other words, this pipe size is 200 and the change in height is about 1 meter or something like that. Then this is the length. Okay, and then this is the point. We talk about point last time from point 2.3 to 2.2, 2.2 to 2.1, and so on and so forth. From point 2.3, 2.2, 2.2 to 2.1. Then 2.11 joins it. From 2.1, it moves to 0.2. 0.1 joins it, and so on and so forth. So here, if you want to design for a runoff, you have to do what we call catchment characterization. In this catchment, 63% of the space is gardens and park. And the runoff coefficient is 0.1. Our letter will show us, you can just go online and say runoff coefficient table. Let me show us. If you go online, say coefficient of discharge. Okay, look at it. Call it coefficient of discharge. Look at it. No. So you can click on any table. You can say image. It will tell you every material, their equivalent runoff coefficient. Name any material or coefficient of runoff. So if you go now, let's say for instance, look at this material. If you click any material, look at this material. It will tell you, it will give you the runoff coefficient. Look at it. It says land use. It says built up area. Runoff coefficient is 0.9. It says agricultural place, 0.4. It says open land, 0.6. It says forest, 0.15. What this thing is saying, this coefficient is saying is that built up area means 90%. 90% of the runoff, water that falls will generate runoff. Okay, while forest, only 15%. Let me check the list. The list is say evergreen to semi-green forest. Water cannot flow. Have you seen where they say water is flowing in the forest? No, because if it is green, evapotranspiration will take place, deep filtration will take place, wetting will take place. So many things will take place. So if you go to another chart, I want one of them to open for me. All these ones are in papers. Look at it, they're in papers. This one says ResearchGate. So you can see there are so many of them. This one is university material. Oh, hey, look at this one. See, you say airport. You say airport has coefficient of 0.8. Built up areas, in this case, is 0.86. Cultivated area is 0.15, and so on and so forth. Let me check which one is the highest. Well, the highest is industrial area. For me, roof is usually 0.9. In other words, 90% of the rain that falls will generate runoff. So we can say it has a high runoff coefficient. That's how we speak it, okay, technically. Then the streets is the whole catchment is made up of 2%. 2% of the catchment are made up of streets, and the runoff coefficient is 0.9. The roofs, okay, or the houses, the footprint of houses is about 20% of the total catchment, and the runoff coefficient is about 0.95. Otherwise, 25% of it will generate, it has high runoff generating capacity. Then others, which is unaccounted for, is about 0.2. Okay, so now there's what we call, so ideally, one will expect you to take the average. You just take the average of the whole runoff. That becomes your own runoff. That's what we call catchment characterization. You have to characterize the catchment and come up with one value. Because the green area is generating 0.1, 10%. Okay, the streets are generating 90%, the roof are generating 95%, others are generating 20%. So you need to take an average. However, there's what we call mean weighted average. Weighted average is a better form of average. Weighted average means this park and garden that has 3%, we have more influence on the mean. Let's leave that apart now. Now, the other parameters I need to design this catchment is the design storm. What is design storm? For rural area, we say the design storm is 10 minutes. Okay? We say the design storm is 10 minutes. Then the population density is 100 capita per hectare. 100 capita. In other words, we expect to have 100 people for every 1 hectare. In my view, that's a very low density area. The place is a virgin area, have not been designed. So they are giving you the design parameter that place is 100 people per hectare. So assuming there are 10, you know, if 1 hectare is 10,000 square meters. So if you divide it into 10 square meters, they're telling you they're expecting 10 people per plot. If you look at it, that's what it means. Then water consumption is just an assumption too. It's 130 liters per capita per day. So we're assuming the water consumption to be 130 liters per capita per day. And we're assuming a peak factor. There's what we call peak factor, it's just like safety factor. In water reticulation, we call it safety factor. But in stormwater and sewer design, we call it peak factor. Well, it's the same thing anyway. It's peak factor. Peak factor is a factor at the highest time when you had anticipated full use. In a residential area, peak factor usually occur by 7 in the morning, 7, 8, and then 7, 8 in the night. There's what we call parasite water. Parasite water is just a safety factor to capture in unaccounted water. That's what we call it parasite. I told us that if it's raining in Abuja, all the sewer line, the discharge from the sewers will increase. Why? Because of pipe breakages of the ground and groundwater entering the pipe. So normally you see increase in discharge. And there is some areas where there is hole and water is just pouring in. And then the pipe roughness is 1.5. So in designing a sewer system, how do you choose your pipe? Your size of your choice of your pipe depends on the discharge, depends on the slope, it depends on the roughness of the pipe material you're using. think we've all done this before. For a combined sewer, the wet weather flow is you combine the dry weather flow and the stormwater flow. So for the discharge, for the storm, no, sorry, for the wastewater, how do you calculate the wastewater? You simply multiply the wastewater discharge, multiply by the population density, multiply by the safety factor, and then you add infiltration flow. So here, this is the wastewater discharge. This is the population, the land use intensity. And then this is safety factor of 2, then plus 0.1, which is just a safety factor. I will get 0.401 liters per seconds per hectare. So this is the amount of wastewater that will be coming in this catchment per hectare. You need to divide, you need to get the unit value. So this is the unit value. If you now multiply the unit value by the area, it will give you the total discharge. That's what it means. Okay? So then for storm, so remember this one is for sewer. For stormwater, we simply multiply the rainfall duration by the area of imperviousness. The area that is impervious, not the area that is the area that's impervious, that's the area that's generating runoff. However, if you want to get the impervious area, which is A imp, you simply multiply the total area of the catchment by the runoff coefficient. So if I want to get the area of imperviousness of a place, all I need to do is to get the total area, multiply it by the peak runoff coefficient. That will give me the area. So if I see that the peak runoff of a place is 0.5, it simply means that only 0.5 of that area is generating runoff. So if the area is 100 square meters and the runoff coefficient is 0.5, it means the impervious area, it means the area generating storm is simply 50. So I'm not going to use 100 in my design, and I'll use 50 because that is the runoff coefficient for that area. So that is that. So what you see here is what we call the mean weighted average of this value. This. If you take the average of these things, it will not give you the true mean, the true average. But if you multiply 0.1 by this, 0.9 by this, 0.9 by this, and then you divide by 100, it will give you a better representative of mean. But just know that the average we got is 0.371. That is the average runoff coefficient we got for this catchment that has different coefficient of runoff of different elements. So, moving forward, in stormwater, how do you choose your duration and intensity? Because here it says arrow underscore DN. This DN means duration and frequency. In other words, the rainfall value at a certain duration, which I say is always 15 minutes, and at a certain return period or frequency. So here we say that if you are designed for rural areas, your return period you use is 1. If you are designed for surcharge, you use 2. If you are designed for flooding, you use 10. So you can see that if I'm designing for flooding, I'll use a higher return period. For residential area, just use 2. Then for a higher value, surcharge is a situation whereby the thing is allowed to surcharge. It's allowed to impound, and then it will go down again. Okay? You know, surcharging is allowed. That is where you are going. You see it rains. You come out, you see water everywhere. Within a few minutes, the water will percolate. Is it allowed or is it not allowed? So if you are designing for flooding, it's a different game. It means you are designing for worst case scenario. So in that case, you use the value of 20. The time period will be 20. If you are designing for city centers, you either use 1 or 5 for your normal storm design. And then for flooding, you design against 50 years. you're designing underground facilities, for normal storm, you use 10. Why 10? Because you must not allow underground to flood. In Europe, they make sure that the flooding does not affect the underground, because if there's flooding underground, the catastrophe will be massive. So because of that, you use a higher return period to do your design. So I've said this before. I have also explained this before, that before runoff occurs, there must be wetting, there must be drifts, there must be evapotranspiration, there will be stoppage design, and then there will be filtration. That is why only a small quantity will come as runoff. Also, depending on the slope of an area, you can also, depending on the slope of an area, you can also, what do I call it? Depending on the slope of an area, you can also see what duration you should use. What duration you should use. Hold on, gentlemen, just give me a few minutes, please. Let me respond to one of us. Okay, let's continue. So that is that. Okay. So when the slope of the area is less than 1%, and the paved area is less than 50%, use 15 minutes. But for now, I would, from experience, I'll ask you to ignore this. Okay, you can ignore this for now. Rather, just use 15 minutes. Sorry, gentlemen. One of us is really having issue logging in. I think I have tried to tell him to use I don't know how to help him. Okay. Okay, let's continue, gentlemen. Sorry for that distraction. So let me emphasize this again. Total runoff is the rainfall intensity, which you read off from your IDF, multiplied by the impervious area, and then multiply by the area of impervious. And the way to get your area of impervious is by multiplying your catchment area by the coefficient of runoff. So, for example, we have 126.3 liters per hectare per seconds per hectare for a runoff of 10 years and 10 minutes and 1 year return period. Okay, we say that if the flow time is longer than 10 minutes, it's the only part of the catchment produces runoff. Okay, it's a discharge, largest discharge occur when rain duration equals flow time. I'll still explain this later. This is very important. Why are we using 10 minutes or 15 minutes is because your maximum discharge occur when the flow time is equal to the duration. In other words, what flow time is, what time does it take water to flow from where it fell to the outfall or to your drain, to enter your drain. I'll still explain when we start the real calculation. Okay, so these are the steps we're going to be taking. All these things now will be for next week. Okay, because from next week we'll start doing the calculation proper. Let me not bore us with that now. But it's a very simple thing. You choose your frequency. Let's leave this for now, gentlemen. Okay, so next week we'll go into the calculation and then we'll use our what do you call it? Our rational method. So I think we have done a lot. I don't see anything to be done again here. I've explained the sanitary sewer. I've explained the national method. I've explained the hydrology and the hydraulics. And I think that's all for now. That's all I can say for now. So I've laid the foundation for what we want to do. This is a material I saw online, which can also be important for some of us. I think it should be a university something. Okay, it's a course. I don't know which course it is, but I think some of us might wish to go through it. Just try and go through it, and there's quite a lot you can learn. Okay, look at this formula, CIA. This CIA simply means this is the coefficient of runoff. I is intensity, and A is surface area. That will give you your discharge, your runoff. Okay, good. With this background I've laid, it is easy and it is very simple. So this is our storm discharge. So once again, let me explain. Let me use this to close. This is your core materials you need for you to excel in this course. One is Nigerian Code of Practice. If you are doing anything with runoff rainfall, you must have this code of practice. This code of practice, like I said, is something that I look at it. This federal government of Nigeria. It was developed in 2013 by the Federal Ministry of Works. Look at it, drainage design. Federal Ministry of Works. Highway design manual. Yes, highway manual, part 1. Highway manual, part 1. You need it. Because here, I think the last design I did some time ago, there was none for Abuja. So I interpolated the value I got for Kogi and the value I got for Kaduna, and I used it. And that is about 140 millimeter per hour for a 25-year flood, a 25-year storm for Abuja. Okay, and the place I designed, I use a runoff coefficient of 0. The client told me to the consultant engineer who I'm working with, so I should use 0.9. I told him, I said, that area is a local area. We're going to use 0.7. So we use a runoff coefficient of 0.7 to do our design. Why? Because we expect that 30% will infiltrate. We expect that only 70% will contribute to runoff, because it's a very virgin growing area. It's not like a built up area or like Ikoyi or central area in Abuja, no, or Gariki, no. These are like places like Lugbe, Maraba. There are a lot of farmlands, there are a lot of green area, there are a lot of parks. So if I use 90%, my size of my drain will be so big and so massive. Whereas the whole place is still more like a virgin area. So this is your highway design manual. So if you go through it, please, as a foundation for this course, then you have shown you how to read the design manual. Look at the one for Enugu. So assuming I want to do a design for Enugu now, I don't need to start going to Enugu to ask somebody for rainfall data for Enugu. No, federal government has spent billions. Okay, look at Calabar. Calabar, for instance, if I'm designing for storm, okay, this is 15. So for 15, for 2 years, Calabar is about 125 or 120. So I can use 220 millimeter per hour to do my design. But if you're not designing for somebody say, oh, I want you to use 10 years to design period, then I'm talking about 170. So that would be quite very massive. So that is how to use it. So on the vertical, you have millimeter per hour, okay, which is your rainfall intensity, okay, and then on the horizontal, you have it in hours, which start with minutes anyway, 10 minutes, 15 minutes, and so on. So if you go on, you see all the cities in Nigeria. If you didn't see it in this one, you go to the second one. It continues there. Yeah, continue with Yola. So if there's any takeaway from today's class, it is this manual that I'm giving you for free. Go and study it, go and look at it, so that you don't need to be starting around people asking for rainfall intensity of the different cities and the different areas. Very, very important. Then tomorrow, next week, this is a design calculation for SIWA. We'll do it next week. Okay. That example I gave you, I'm going to design everything here. Okay. After doing for SIWA, we'll do for storm. So these are the two components. We talk about stormwater on one side, we talk about SIWA on the other side. Please, any question?
Please kindly manual with you so that we can also.
Sorry, sir. I can't hear you, sir.
Kindly share the manual with.
The manual is is in the group, sir. The manual is in the group. I've shared everything in the group.
Okay, sir.
Yes.